So, good afternoon, everybody. Welcome to sort of snowy and not so good driving weather afternoon of Chem 170 with your host, me, Dr. White. Hi, everybody. All right, important announcement. I just thought about 3 minutes ago. I checked. I will be postponing test number 1 by 1 week. I will put out an email with the new date, but because we lost the first week, because they started a week later, I will now be postponing test number 1 by 1 week, which is why I always put down tentative test schedule. Because if we were face-to-face, what if we got knocked out a whole week because of snow? And that happened a couple of years ago. So that's the first thing. Let me give you today's game plan. First of all, I will be going through the Chapter 2 Alkynes problem set. Will I do all of them? No, but I'll do some. And if you have any questions or requests, ask. Remember, there's no such thing as a dumb question in my universe. Oh, I looked at my monitor. I'll never be a TV announcer. Or in my world. So after that, we will continue on with alkenes and alkynes. And then about 45 minutes before the end of the class, I will start lab number 1. I'll go through all that. Now, normally on a Wednesday lab day, if we were face-to-face, I'd go 50 minutes. Then we go into the lab and you do the lab and you get out in about an hour and a half, though you're given 2 hours. But since we're not, what we'll do in the future is I'll go about an hour or so, take a break, and we'll do a lab, and you'll get out early. Shh, don't tell anybody. But anyways, that's how it would be face-to-face. But because I lost that first week, 3 full hours, I'm going to go longer today. But you're supposed to be here till 3:50 anyways. I got you. But oh, Sargon, that's why you're here. Oh, good to see you. All right. I don't know how the weather is where you are, but here I'm in Schaumburg. We've got about 3 inches or so. I taught this morning people who at College of DuPage, which is in DuPage, way south of us, and they got a lot more snow. All right, let's get going. All right, everybody see alkanes problem set, practice problem answers. So let's go through a couple and let's do D. And the question is, how many carbon atoms are in the longest chain, which is an important skill you should have. Now, if we look at D, I can count. Notice I was a nice person. I didn't even put in the hydrogens to confuse you at this point. This carbon is bonded to that, to that, to that, to that, that, and that's 6. But remember, when we're looking for the longest chain, just like chains that are linked together, like a bicycle chain, or not to get personal, this my gold chain, which you couldn't see, you can move them around. So another chain would be 1, 2, 3. This is number 4. And then it's linked to this carbon 5, this one 6. And if we want 1, 2, 3, 4, 5, that would be a third chain. So either way you count it, and you get the same name later on if we did IUPAC, the longest chain is 6. Now, if we look at E, Dr. White was sneaky. Chains don't always have to be across. Usually they are the longest chain, but doesn't have to be. E and F shows you that. And if let's do F, we look at F, our number of chains, 1, 2, 3, no, 1, 2, 3, 4, 5, 6, no, but look at the longest chain, 1, 2, 3, 4, 5, 6, 7, 8, 9. There's one other chain I didn't put here, 1, 2, 3, let me do that again, 1, 2, 3, 4, 5, 6, 7, 8. So the longest chain was 9. And you need to be able to do that in order to develop and create the IUPAC name for molecules. Any questions on others on number one? Always feel free to ask. Now, one thing I should mention, my hearing isn't the best, which means if you say a letter of the alphabet, I might not understand it. So if I ask you to repeat it once or twice, not 12 times, hopefully never, please bear with me. That's my problem. Words I can usually make out. If I don't understand all of it, I can guess most of the word. Alphabet is just one letter. All right. Important skills you should have in nomenclature. Remember, nomenclature is naming, and that's give the IUPAC name for the following molecules. IUPAC means official. I will never ask on a test, but I think it's cool to say International Union of Pure Applied Chemistry. Any of you ever see the old TV shows, The Man from U.N.C.L.E.? United Network Command for Law Enforcement. I thought that was cool too. So did the people who created that show. But anyways, well, I just did a generation gap thing on you. How do you give the IUPAC name? First, you find the longest straight chain. And if we look at oh, it's your old friend propane, 3 carbons. And let me open it up because I do not have it open. Actually, let me do it a different way. Hopefully you've all by now or soon by next Monday have memorized this chart. And you should know the name and the number of carbons for each name. And propane is 3, and so on. Now, if we go back to the problem set, notice this has 9. Now, I wrote or. I will not be using the parens. Parens means you have a parenthesis here and here. Notice the subscript 7 here. That means there's 7 CH2s like this. I won't use this until way later into chapter material on test 4 when we get into big molecules like fats and oils. But I just thought I'd show you that. Now, if we look at F, the question is, what's the IUPAC name? And now you have to do something a little different. First, you have to find the longest chain. Longest chain was a cross. I made it easy for you in this one. And it's 9 carbons. The root name, 9, no name. Now, as soon as you have that, what's left over is right here, CH3 and CH2, CH3. Those are alkyl groups. I'll never ask you on a test what's an alkyl group, but you need to know the names of the alkyl groups. And if we look, you can find on D2L that I have this cleverly named key alkyl groups file, both as a Word file and PDF. We have methyl 1 carbon 2 is ethyl, 3 to the end of the 3rd carbon bond to chain or ring, and propyl, to center isopropyl, and to the end of 4 carbons, N-butyl, to the middle of a carbon that has 4 CH3 groups on it. That's called a tert-butyl. Starting next week, I'm going to be a lazy organic chemist, and we are. I'm going to call it a T-butyl group. You should know these as well as you know your first name. I'm assuming you know your first name like that. Oh, that was quiet today, like that. All right, let's continue. So what do we have here? CH3 methyl group, CH2, CH3 ethyl group. Next, you have to find what carbon are they on. You go to the ends of each chain. Never stop. Excuse me, common mistake. Students will say, oh, this is the first alkyl group. I'm going to call that carbon 1. Wrong, wrong. big time wrong. What do? You can only start on an alkane straight chain from either end. Those are the only two positions that could be carbon number one. And you number it in such a way that the alkyl groups have the lowest number. In this case, the methyl group is on 2, the ethyl group is on 4. Now, you put the alkyl groups in the order of alphabetical priority. Use the alphabet first letter of the actual group. Now, I'll explain something in a little while, but this is ethyl, so that's in front of M-methyl, and therefore it's 4-ethyl, 2-methyl. I will not hold you to this rule on my test. You put 2-methyl, 4-ethyl, even though IUPAC-wise that's not correct, I'll allow you to do that. Now, important thing, when you have either iso or N, that's not the letter you use for alphabetical order. For iso or N-propyl, it's P. For N-butyl or tert-butyl, it's B. And that's why this, the correct one is 2-methyl-4-isopropyl nonane. All right, let's move on. What do we have here? A ring. You count the benzyl in a line. There's 6 of them. That would be hexane. Because it's a ring, it's cyclohexane. Again, the prefix, the part that goes in the front of the word, that's prefix, is cyclo for rings. So you count the number of carbons, 6 hexane from this table, which hint you've learned, or soon by Monday we'll learn, and 6 carbons hexane, but it's a ring, cyclohexane. Now, when there's only one alkyl group on a ring, you don't use a number, because every carbon, no matter if it's here, 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 all you're doing is rotating the ring around, will always be carbon 1, so you don't need to do this. 6-member ring, cyclohexane, and then 3 carbons, center 1, 3 carbons, center carbon, isopropyl. And that's isopropyl cyclohexane. All right, public service announcement from me, your host, and that is on test number 1, students for this type of name forget to put the word cyclo. And isopropyl hexane is different from isopropyl cyclohexane, as to me, your nose and your ear are different. If I were to ask someone to draw your ear and you drew your nose, would they get partial credit? What was on my face? No. And same thing here. If you don't put the cyclo for cyclohexane, or if it's a ring like here, cyclopentane, you get 0 points. One of the hard things about organic is, unlike general, and I'll answer your question in a second, is you don't get that much partial credit in my class. I like to give it, but it's usually right or wrong. And if the root name is wrong, you get nothing, even if you get the alkyl groups right. Sargon, do you have a question?
Yeah, I do. Do the 2 words need to be separated by a space, or can they be one word?
Yeah, UPAC rule is letters or words like that are not separated by a space. But I don't think any of you are really going to be typing out the answers. And even if you did, if you had a spacers too, I'm not going to take off points ever. When I grade a test, I don't sit there and say, oh, how can I take off a lot of points? No, I say, I hope students do well. If it's wrong, yeah, I'll take it off. But if there's any way I can say, yeah, that's right, I'll give you the points. That's just who I am. Speaking about my test, I see there's, Jacqueline, let me get to your answer in a second. That's a good question. Oh, let me do this first. All right, let's talk about my test and that wire there is. Give me a second. That looks awful. That's better. I didn't want you to think I'm a robot. I am Dr. White. Never mind. But anyways, couple things, important things about my test. First of all, I write tests, and if we were face to face, you have 55 minutes. Most people are done within about 35, 40 minutes if you study and do the practice problems. If you do neither, I could give you the whole week and you still wouldn't know what to do. But I write my tests so every student should have plenty of time to finish. Second, every question on my test, every question except what's your name, that's the question where you have to put down your name. I have covered the concept behind that question at least twice in a lecture. Usually it's a lot more, but at least twice, that's a guarantee. I don't have, we never talked about that. I never do that because I follow my golden rule of teaching was don't do to students what I didn't like done to me. And yes, I was a student long time ago in a galaxy far away. All right. And when we do have the test, I'll explain it more. But at the end of our time together on Zoom, it's a lab day. All my tests, except for the final, which is not a test, will be on Wednesdays. That gives me time to grade them because I don't use multiple choice on any test in this class. Never have, never will. I hate multiple choice. They're designed to trick you, not for you to show me what you learned. And I will always give back to tests or have them graded and go over the answers in class the next Zoom meeting, which will be a Monday because I'm always giving on Wednesday. Now, one other thing that I've done was on Zoom is I do not, when I go over the test answers, I cut it out of the video. I like that special effect. I cut it out of the video, but if you can't make it to class, come and see me during my office hour, and I'll be more than happy to go over any questions and answers on the test. I just don't want my test floating around YouTube for all the rest of eternity. All right, now back to the question one of your colleagues had, and let me use the whiteboard. Oh, look out, I'm having a good ring drawing day. Just like you have bad and good hair days, I have bad and good ring drawing days. Now, the question was, why don't we call this 2? And let me draw one more structure that I should have drawn first. These are all the same structure. Why? Well, let's take a look at molecules. They are not glued on a piece of paper. They exist in 3 dimensions and they can rotate. Now, if I said, close your eyes, and you did, first look at this, it's my hand. I said, close your eyes. I did this. I said, open them out. Oh, look, it's something different. You say, no, you just rotate your hand so many degrees. And if I said, oh, look at this, and I go like this, oh, it's something different. No, you just rotated and moved your hand around. Well, it's the same with the rings. And if we look at what I drew, all that's happening is to go from here to here, this is this rotated. Same thing, to go from here to here, this is this rotated 180 degrees. And that's why they all are the same. And when there's only one substituent on a ring, you don't use a number because technically every carbon is 1. And since we all know that, why do we have to write down a number? And that's the reason why that's not 2-isopropyl cyclohexane. And Jacqueline and everybody else, well, first of all, thank you for your question. So I'm sure other of your colleagues had similar thoughts, and now you all know how to do it correctly, which is a good thing. At least I think so. All right, now, this one is a little tricky. Okay, we have a ring, 5 carbons, pentane. So ring, cyclopentane. I have a T-butyl group or tert-butyl and an ethyl. Now, the way IUPAC has it is when you have alkyl groups on a cycloalkane, a ring, know their functional groups, then the carbon with the highest alphabetical priority is 1. Therefore, remember, tert you ignore, this is a B, butyl, therefore the correct IUPAC is 1 tert-butyl, 2 ethyl. However, if you get the numbers switched, I will not take that off because I'm not holding you to alphabetical priority rules. So actually, on my test, there'd be 4 different answers. You have 1 tert-butyl, 2 ethyl, you could have 2 ethyl, 1 tert-butyl, and you could have numbers switched, and you could have the order and numbers switched. I would mark those all correct. Oh, I forgot to tell you.
Excuse me.
Did I tell you, hold on one second. Did I tell you I'm this close? I mean, really this close to the person who grades the test in my course? Me. All right, somebody had a question?
I just wanted to ask.
I got to talk a little louder, Vivian.
Can you hear me right now? Can you hear me?
Not really. Do you think you could try the chat and type that out? For whatever
Okay.
reason, your mic or something is not working, a technical problem. I'm going to move on. When I get your question, I'll answer it, okay? Now, when it comes to nomenclature abilities or skills, which means questions I can ask on a test, hint, there are 2 things. One is here's the structure, give the IUPAC name. The other is here's the IUPAC name, draw the structure. And here, butane, you should know from this butane 4 carbons. The other thing you should know, ooh, I better do this full screen. There's 4 bonds to carbon. Oops, let me finish it. Remember, this is your friend. On test 1, 2, 3, 4 in the final, the students had looked at structures they had drawn, and the most of the good part of the test, you do have to draw structures. If it didn't have 4, yes, 4, 1, 2, 3, 4 bonds to carbon, it's wrong. I remember one time, student had 6 or 7 bonds to carbon in a structure, and it took me a couple minutes to stop laughing. I said, oh, come on, give me a break. Remember, 4 bonds to carbon. Ooh, I must have been doing something, get a callus there. But anyways, remember that. So if we go back to this, CH3, CH2, CH2, CH3. Now, if we come over here, how do we know what to write for 2, 3? And I forgot the dash, it fell off, I'm sorry. Dimethylhexane. You start from the right and move left. Hexane. You've learned hexane from this chart, 6 carbons. Methyl. You've learned methyl from this chart, CH3. And di, which I don't have on a chart, and let me see. All right, now I see your question. All right, for tert-butyl, you ignore the prefix. You consider that a B. And that's why that comes before ethyl. And that's also why I'm not going to hold you to that on a test. Vivian, If that works, okay, thanks, you got it. Good, and thank you for your question. Sorry, your microphone was causing problems. Now, I don't have on a sheet, I did it in class, let me do it again. Remember, when you see di, that means 2, tri, that means 3. Oh, I better be subtle. Okay? You should know di as a prefix means 2, tri means 3. Actually, there are more of those, but I've never had to use them in my career, which means you probably will never see them except for one really joke involving tetra, which I'm not going to even do in this class. It's so bad. All right, let's go back to the problem set. And notice we're trying to figure out how to draw this hexane 6 carbons, methyl CH3. Di means there's 2 of them. And what carbons are they on? 2 and 3. And I started counting this way. This is 2, this is 3, and there's 4 bonds of carbon. Now you could have rotated it and made this carbon 2, this carbon 3, and put the methyl groups, and that would be totally correct. Now, I made a mistake when I first wrote this, and I didn't have a chance to correct it on the actual sheet, but I did on the problem set. And that really should be 1 tert-butyl, and that should be first, and 2 ethyl second. But, and here's one way of drawing it, which none of you did. So I'll show you the way to draw 1 tert-butyl, 2 ethyl cyclopentane. The way you did it. All right, how did you code this? Start from the right and move left. Pentane, 5 carbons, cyclo, ring with 5 carbons. Whenever I see a, ooh, I'm having a real good ring drawing day. Whenever I see a cyclopentane ring, I think of the greenhouses in Monopoly. You guys ever play Monopoly? By the way, when I was 5 or 6, my sister was a couple years older and we were both sick at home. We'd play Monopoly a lot. And whoever went to the bathroom, the other person always stole from the bank. We played cutthroat Monopoly. But anyways, so I have on carbon 2, an ethyl group, carbon 1, a tert-butyl group. And most of you probably did this. Called this carbon 1. And called this carbon 2. And now I know there are 4 bonds to carbon. So I can put in my hydrogens. And that's how it's another structure. The one I have is just a different rotation, just like my hand. And notice on J, I have how would you write this? Start from this end, octane, 8 carbons, methyl CH3, tri means 3. Remember, prefix di is 2, tri is 3. And where are those methyls on 2, 3, and 5? So this is carbon 1, end of the chain can only be 1. not anything in the middle of the chain. This is 2, this is 3, 4, and this is 5. And it's, oh, look, it's your old friend propane. All right, now, number 2, give the reaction product or products to the following. I got lazy, I didn't do it on here. Let's look at the first one, propane plus oxygen. How do you do something like that? If we look at this, what kind of molecule is that? It's an alkane. Only carbon, hydrogen, and not in a ring, but it could have been a cycloalkane. And you're reacting with oxygen, and you've learned this general reaction, you get CO2 plus water. It doesn't matter if you put water first and CO2 second, the order doesn't matter. And you get heat, but I'm asking for products. So if this is an alkane, these are going to be my products. So the answer is this. And in my class, and most time in organic chemistry, we never balance chemical equations. The only time you do it, if you have to figure out charge weights. The question is, can you balance it? You can, but you're wasting a lot of time on a test that you could spend on other things. So if you want to, I'm not going to mark it right or wrong if you balance it right or wrong. Yes, I know how to balance it right correctly, but I'm not going to teach that in this class. You should have had that in general chemistry, and you'll see later on when we do more complex equations, chemical reactions, you'll be making structures where you don't want to waste time balancing each equation. On test number 1, and I'll put this out in an email a week or so before, but I'll tell you now, my tests for this class have 3 areas mainly. First area, general knowledge. What would be a good general knowledge? Oh, I don't know. How many bonds does carbon have? We all got that right. 4. Or other things. Next, nomenclature questions. And the 2 main nomenclature questions are, here's the structure, give the IUPAC name. The other one is, here's the name of the molecule, draw the structure. And the third type is reactions. And I'll talk more about, but the majority of that type of question is, give the product or products for the following reaction. And if you've got a bunch of them, you don't want to waste time balancing each and every one of them. That's your choice, but you don't have to. Now, if we look at B, it's octane, same general reaction. Alkane or cycloalkane, oxygen, CO2 and water. That's it, CO2 and water. Same thing for C, cycloalkane, this is cyclohexane. Oxygen, you get CO2 and water. And what I was trying to illustrate on this question is, know your functional groups, know your type of molecules, because they undergo the same type of reactivity. You need to know if you want to do good on tests, and I'm going to assume, unless somebody emails me or tells me in private that they want to flunk my course. I hope nobody's like that. Gee, I hope not. But anyways, if you want to do good in my class, not only do you need to know the alkane names, the alkyl group names, and the IUPAC rules, you also have to know these type of general reactions. And how do you memorize that? Well, your best way I know, and I've talked about it, is you write it down 5 times and say it. Each time you write it, alkane or cycloalkane, and you actually write it, plus oxygen, arrow, CO2 and water. And then you say it. alkane, cycloalkane, oxygen, CO2, and water. Then you do it 4 more times. Then a couple days later, you do it again, you'll find you remembered it. Plus, you do my practice problems. That gives you more practice. And that's why students do well in my class. And you hear about horror stories in other organic classes at other schools. In fact, if you look at ratemyprofessor.com, 2 of the last 3 posts, students who came to took my class, one of them I didn't realize till the end, she told me she had flunked the first semester, 2 semester organic twice. Took me for the 1 semester because she heard about me through word of mouth, and she did quite well. Another student took a 1 semester, another school flunked it, took it in my class, she got an A. That's because I show you my students, you people, how to practice. All right, any questions? Any part or anything with alkanes? Ooh, I got a question. Anybody happen to drive by a gas station and think about alkanes? That's what they're selling. Anybody happen to look at either when you turned on, if you have gas, your gas stove, think about, or your furnace went on and you felt nice and warm and wherever you're living, or if you had hot water when you took a shower or washed your hands, say, oh, that's methane, natural gas, that's an alkane. Anybody think about propane for your barbecue as an alkane? How about Vaseline or baby oil, or half the weight of a candle, paraffin wax? Those are all alkanes. And when you're not in my class, think about organic chemistry. Trust me, it won't hurt, and it's all around you. I stole that from SpongeBob. You see the one where he did imagination? Good. Guess what? I do it all the time. But I'm an organic chemist. All right. Thank you for sharing that. All right, let's get back to alkenes and alkynes. Now, I believe I went through halogenation on Monday. Didn't I cover that? Let's do it again. Just go back. When you have a double bond and you react it with halogen gas, remember X is the abbreviation for the halogens fluorine, chlorine, bromine, or iodine. You should know, general information. A double bond has 1 pi bond, and 1 sigma bond. And you can break pi bonds like that. Sigma bonds, single bond, you're not gonna, that wasn't scientific. No, you won't break those. No. And if we break the pi bond, each carbon of the double bond gets a halogen. And then so I think I went through this, but I'll let you try this one because I haven't let you shared any of the fun yet today. So what would be the organic product, 3 points for the following reaction? Now, do you break carbon-carbon single bonds? No. By the way, I do the same thing face to face. No. Let's try something. All right, looks like everybody's done. Let's do this. Let me just get back to here. Does everybody see the whiteboard now with the problem? Thumbs up, people. Thank you. All right, let's do this. When you look at an organic molecule from henceforth, you should always look for what's different. What's not a carbon-carbon single bond or a carbon-hydrogen atom. And right here, 2 lines between a carbon. Remember, every bend in a line in a ring is a carbon. That's a double bond. Everything else is carbon, a hydrogen, carbon-carbon single bonds, and this is coming along for the ride. What's this? Iodine, and that's a halogen. And we know X could have been fluorine, chlorine, bromine, ooh, that's a lousy beat, or iodine. And you break the pi bond, and each carbon gets a halogen of the double bond. Well, here are my 2 carbons, double bond. Do I break carbon-carbon single bonds? No. So I still have my methyl group on that ring. These are my 2 carbons of the double bond. Each one gets a halogen. The halogen is iodine. And there you go. Now, you could have also written it this way. And that's how you do it. Remember, it's important when you're doing chemistry, organic chemistry, and showing the structures. Everything I do here, this is called the structure. If I could spell it right, sorry. Structure, where you put atoms is important. If you had put this iodine over here, I'd mark it wrong because you don't get that. Those go on the 2 carbons of the double bond. All right, let's do one more. That's Cl2. What would be the organic product or products for the following reaction? 3 points each. You're doing organic chemistry. Hopefully it's not that painful. Actually, it shouldn't be painful at all. By the way, person who just made a comment, everybody else, by the end of the semester, I'll have you looking at a lot of things and say, ooh, that's organic chemistry. And more importantly and excitingly, you'll know what it is, including all the food you eat. If we were in class face to face, I could look at you people and watch and tell when you're done, but a little guilt here. You don't have your webcams on, so I can't tell. Most of you. All right, let's do it. If you look at this molecule, look for what's different. What's not a carbon-carbon single bond or carbon or hydrogen should get your attention immediately, like red lights flashing in your rearview mirror, like from a fire truck so you pull over. A double bond. What am I reacting double bond with? Chlorine gas. Chlorine is a halogen, X, and there are 2 of them. It's diatomic, di meaning 2. Oh, you know, di. atomic atoms. And remember, X can be chlorine, bromine, iodine, or fluorine, the halogens. You break the pi bond, and each carbon of the double bond gets a halogen. Do you break carbon-carbon single bonds? No. So I have 1, 2, 3, 4, 5 across. 1, 2, 3, 4, 5 across. On this carbon, I have 2 methyl groups. They're still going to be there. What are my 2 carbons of the double bond? These 2. Look out, I'm going Technicolor on you. And now we know, notice I also broke one of the bonds, the pi bond, because that's what this tells us. And now I know each one of those carbons gets a halogen, and the halogen is chlorine. Chlorine counts as 1 bond to carbon, so immediately I know there's 4 bonds to carbon. I'm done. And that's how you do it. These chlorines have to be on these carbons, not anymore. Now, if you look at this reaction, let's write them down. 2 reactions I've taught you. Hydrogenation and halogenation. Oops, had mind on halogens on hydrogen. Let's get that right. Notice this is symmetrical addition. What I mean by that is, what am I adding to each carbon? The same thing. In the first example, each carbon gets a hydrogen. In the second example or general reaction, each carbon gets a halogen. What happens if you're not adding the same thing to each carbon? And that turned out to be a very important question that needed to be answered. And we call that unsymmetrical addition reactions. And a famous Russian organic chemist, Markovnikov, came up with a rule. And because of the great discovery he made, we name it Markovnikov's rule. I will never ask you to spell Markovnikov's name or write down his rule other than know how to use it. And the rule is, when an unsymmetrical molecule, the form of HA or HQ, is added to an unsymmetrical alkene, double bond, hydrogen from HA or HQ becomes bonded to the unsaturated carbon that has the most hydrogen. What? Well, guess what? I'm going to do something they do in the movies, a cliffhanger. You're going to have to wait 5 minutes to find out about this, because it's time for a break. Let's take a 5-minute break. I'll see you at 1:55, and you'll learn about Markovnikov's rule. Oh no, I'm running late. Time to get started. I just thought of something I hadn't thought about. Did anybody ever play hide and seek? Remember, come out, wherever you are. I hadn't thought it out. We used to play some amazing when I lived, a little kid living in Chicago. There are a lot of places you could hide. All right, let's get back to organic chemistry. Now, Markovnikov's rule deals with when you have unsymmetrical molecule. In other words, hydrogen, you have two hydrogen atoms, one going to each carbon. What happens if you don't? Well, let's look at a specific reaction that's called the addition of an acid, actually a halogen acid, to an alkene. Let me rewrite this differently on the whiteboard, because after I wrote those slides, I think this is better. Now, let's look at the following. If you have a double bond and you react with it HX, remember, I can write a chemical reaction like this, A plus B reacting to C, or I can write it like a lot of organic chemists like me do, this, the B over the arrow tells you B is reacting with A, makes C. Now here, X is not all the halogens. It's chlorine, bromine, or iodine. HF, hydrofluoric acid, is dangerous stuff. And you don't want to work with it unless you really, really have to, which means we don't use it for this reaction. In fact, the only time in my chemical career long ago, when I was a bench chemist, I refused to work on a project, dealt with hydrofluoric acid, and I said, no, I don't want to. Do you want me to quit? And I'd already made some major discoveries. And they said, no, they found someone else, and he almost had a nervous breakdown working with dangerous stuff. Now, you break the pi bond, one carbon gets H, the other gets the halogen. And how do you know you follow Markovnikov's rule? Now, years ago, I used to spend the next 2 minutes writing out, oh, that's wrong spelling, let me check Markovnikov's rule. And I just put down M's rule. Well, what is that? Well, I have to show you the best way is with an example. Now, if I were to ask you the following question, say this are part A, give the organic product or products for the following. What do? Well, you look at a molecule and look for what's different. What's not a carbon-carbon single bond or carbon or hydrogen and say, oh, look, a double bond. You don't have to say, oh, look, but you should see that double bond. And now I have a double bond. That's the rest is carbon and hydrogen's carbon-carbon single bonds. That's not going to react. I have HBr, remember the halogens are X, and for this reaction in my class, chlorine in real life too, it can be chlorine, bromine, or iodine. And you break the pi bond, one carbon gets H, the other gets X, and it follows Markovnikov's rule. Well, do you break carbon-carbon single bonds? No. So I start with 3, I better end up with 3. Now, let me teach you Markovnikov's rule. Look at the 2 carbons of the double bond. How many hydrogens does each one have? 1, that has 2. Which is the larger number? Now we're doing high-level math in my class. Hopefully I'll pick 2. The carbon with the most hydrogens of the double bond gets the hydrogen. And the other carbon gets the halogen. So this carbon here has the most hydrogens. It gets the hydrogen from HX. The other carbon, in this case, the halogen is bromine, gets that. And in real life, that's what you get. And that's Markovnikov's rule. Now, if you had the hydrogen bromine switch, I'd mark it wrong because you obviously don't know Markovnikov's rule. Now, something I still remember, and don't ask me why, I don't know why, other than I have a photographic memory and a very good memory. When I first was learning organic chemistry, our instructor, I remember his first name was the same as mine. I can't remember his last. I think it was I now remember Dr. Steuben. And he taught us this, and the way he said, you know how you can remember Markovnikov's rule? The rich get richer and the poor get poorer. And we're talking about hydrogens. The one with the most hydrogens gets the hydrogen, the other one. The other one, he also taught us the same lecture, was bad English, but those that have it get it. Or those that have them gets it. And we're talking about, again, hydrogens. So Markovnikov's rule is the carbon of the double bond with the most hydrogens gets the hydrogen, the other carbon gets the halogen. And here's one for you to have fun with. Am I nice or not? Don't answer that. Oh, you can if you want. Give the organic product or products to the following. If we're in a classroom, I'd say when you're done, look up and smile. But none of you have, most of you don't have your webcam on. I also have done, give me a thumbs up, but this works too. All right, looks like everybody's done. Let's take a look at this. What do? Well, we look at a molecule, look over what's different, what's not a carbon-carbon single bond or carbon-hydrogen atom, gets your attention real quick, double bond. The rest is this carbon-carbon single bonds, hydrogen, nothing's going to happen there. I'm reacting with HBr, halogen, HX. And remember, X can be chlorine, our case it's bromine, or iodine. You break the pi bond of the double bond, so there's only one line. One carbon gets H, the other gets X, and it follows Markovnikov's rule. The carbon with the most hydrogens, the double bond gets the hydrogen from HX, the other carbon gets the halogen. And now we have to do our high-level math. Aren't you amazed how hard the math is in this class? How many hydrogens does each of these carbons have a double bond? This has 2, this has 1. Next, you have to use your high-level math skills, which is a greater number. And this is the carbon that the hydrogen will go to. Do you break carbon-carbon single bonds? No. So I have 4 carbons. This carbon gets the hydrogen. This carbon gets the halogen, which is bromine. I know there are 4 bonds to carbon. The halogen counts as a bond. And I can put in the rest of the hydrogens. Now, you could have written this as CH3. You don't have to, but if you want, I'm not going to mark it wrong if it's correct. And that's how you do. Oh, let's do another one. Now, remember, you'll learn later on to make this kind of molecule. I can then use it elsewhere to make things that you use in your daily life. So think about this as being like a carpenter learning how to use a 2x4 or a nail or a nut and bolt to build things like houses or boats or whatever they build. All right, I'm going to do this one. And the question is, what's the organic product or products are the following? And if you look at this molecule, I have a double bond here. And remember, each bend in the line is a carbon here and here. And I know, oh, double bond, HX, because iodine is a halogen, X equals chlorine, bromine, or in our case, iodine. I break the pi bond. The one carbon gets H, the other gets the halogen, and it follows Markovnikov's rule. Uh-oh, I've got a problem. I don't see any hydrogens there. Well, they are. And by the way, Mother Nature and Dr. White love rings, students don't. This is one of the reasons. Let's look at this carbon. How many lines do you see going bonds to that carbon? 3. How many bonds to carbon should there be? 4. So there's one hydrogen here. Well, let me do something different. We don't show it, but there's one hydrogen there. Let's look at this carbon right here. How many bonds, lines do you see going there? 1, 2, 3, 4. There should be 4 bonds to carbon. 4 minus 4 is 0. This has 0 carbons. And now I know how to proceed using Markovnikov's rule. Do you break carbon-carbon single bonds? No. So I'm going to have my ring, still going to have my methyl group. Now, this carbon right here would get the hydrogen, but we don't show hydrogens on a ring. This carbon right here will get the halogen, iodine, and you could have written it this way also. In an upper level class, which I'm not teaching this and here, how you draw that can sometimes make a difference, but not in my class. Now, let's look at this carbon right here. How many lines do you see to that carbon? 2. How many bonds should there be to carbon? 4. And 4 minus 2 is 2. So even though we don't show it, that has 2 hydrogens. Notice we started with 1, we now have 2. So we actually did add that hydrogen there to this carbon. We just don't show it. And that's how you use Markovnikov's rule with a ring. Oh, I better let you try one. Now we're getting in some fun and serious organic chemistry. I'm happy. But then I'm an organic chemist. I love this stuff. And good news, we're not done yet, so I'm not assigning it. But if you look at the alkenes and alkynes practice problem set, they're examples for you to work like these type of problems. In other words, practice problems. If you're having difficulty, that's allowed. You're just learning it. All right, looks like everybody's done. So let's take a look at this. What's different? What's not a carbon-carbon single bond or carbon-hydrogen atom? Double bond. Everything else, carbon-carbon single bonds and hydrogen carbons. I'm reacting with hydrochloric acid, HCl, which I can show as HX. Remember, X can be the halogens, in this case, chlorine, bromine, or iodine. And I break the pi bond. Remember, this has a pi bond and a sigma bond, single bond. And each carbon, one gets H, the other gets X, and it follows Markovnikov's rule. The carbon with the most hydrogens gets the hydrogen, the other gets the halogen. First of all, I know, do you break carbon-carbon single bonds? No. So immediately I can draw this in, because those come along for the ride. Now, here are my two carbons right here and here. Now I have to find out how many hydrogens are on there. Notice this carbon right here has 3 bonds to it. 4 minus 3 is 1 hydrogen. This carbon right here has 1, 2, 3, 4 bonds. 4 minus 4 is 0. Now you have to use your really high level math skills, which is a larger number. Hopefully you all picked this. Therefore, the hydrogen goes here, but we don't show it. The other carbon with the ethyl group, CH2, CH3, will get the halogen. In this case, it's chlorine. And you could have also written it this way. And there are other ways I could have written it too. And those would be identical. All you're doing is rotating it 180 degrees. And that's how you do Markovnikov's rule, addition of HX, hydrogen, hydrohalogen acid or acid. This is hydrochloric acid, hydroiodic acid. Hopefully you all know an acid is something that donates a proton. Later on, when you need to know about all acids, I'll teach you that again in case you forgot it. And let's continue on. Now let's look at the addition of water to an alkene, otherwise known as hydration. And let me rewrite the general reaction instead of this one. I was trying to be too fancy when I did those slides. Let's look at the reaction. We take a double bond, and here we need a catalyst. And the catalyst is an acid. And in organic chemistry, when you have a number of acids you can use, we use the abbreviation H+. And we're adding water. Hopefully everybody knows water is H2O. But let me show you another way of writing water. H, OH. And by the way, OH, and I'll teach you this again later, OH is called the hydroxyl group. So what happens? You break the pi bond, and one carbon gets the H from water, and the other gets the OH from water, hydroxyl group. And guess what? This follows Markovnikov's rule. The carbon with the most hydrogens on the double bond gets the hydrogen from water, the other carbon gets the hydroxyl group. And when we put a hydroxyl group on a carbon, we call that an alcohol. And later, I think it's 2 chapters down the road, I'll be talking about alcohols. And it's not just the one you find in vodka or other good things in life. By the way, Dr. White loves his vodka. All right, let's do an example. If I take a double, this molecule reacting with acid catalyst, that's what the H+ means, and a catalyst is never consumed in a reaction, plus water, what's the product or products? Well, I look at this molecule, what's different? What's not a carbon-carbon single bond or carbon-hydrogen atom? By the way, in about a week or two, you'll be having nightmares hearing me say that, but it's important. I do that every time I look at a molecule. We have a double bond. What are we reacting with? Acid, catalyst, and water. Let's think of water as HOH. And you break the pi bond. Remember, we have a pi bond there that's easy to break. One carbon gets H, the other gets OH, hydroxyl group, and it follows Markovnikov's rule. And now, do I break carbon-carbon single bonds? No. So I start with 3. I better end up with 3. This carbon has 2 hydrogens. This carbon has 1. Which is the greater number? Time's up. Hopefully all pick 2. Therefore, Markovnikov's rule says the hydrogen goes to the carbon with the most of the double bond with the most hydrogens. It will go there. Remember, the rich get richer and the poor get poorer. The other carbon gets the hydroxyl group. This counts as 1 bond to carbon. So 3 minus 1, 1 hydrogen. And that's how you do it. Your turn. Have fun. Am I nice or am I nice? Don't answer that. All right, it looks like everybody's done, so I better get to work. If we look at this molecule, and I apologize, I should have, when I do structures on a test, my computer software draws them. It's called ChemDraw. What's different? What's not a carbon-carbon single bond? Carbon hydrogen. Oops, one of you should have caught me. Bad, Dr. White. There should be a hydrogen there. Remember, it's your solemn responsibility now that you've lost your rookie status, my class, that if you see a structure and I have it wrong, I don't have enough hydrogens, let me know. All right, double bond reacting with acid catalyst, H plus, and water. Remember, think of water as HOH. Break the pi bond, 1 carbon gets H from the water, the other gets the hydroxyl group OH, and it follows Markovnikov's rule. And therefore, we have to do high-level math. This carbon double bond has 1 hydrogen. This carbon has 2, which is the greater number. Hopefully I'll pick 2. Do we break carbon-carbon single bonds? No. So I have 4 across. This methyl group will still be on that carbon. This carbon gets my hydrogen. This gets the hydroxyl group. There's 4 bonds to carbon. Remember, keep an eye on me. I already made one mistake today. And that's the product you get. If you have the hydroxyl group on a different carbon, it's wrong because you're showing me you haven't learned Markovnikov's rule. Oh, let's do one more. Oh, by the way, I have the fastest mouse wheel finger this side, the other side of the Mississippi River, which means the whole United States, not the world. And if you ever want me to roll back to a slide when I'm part of a slide or whiteboard, always feel free to ask. And it's your turn to have fun. What would be the organic product or products for the following? 3 points each. And don't forget, tonight I have my office hour from 5 to 6:15. And after that, I get to go out and have quality time with my driveway and snowblower. Because I've been teaching all day, I haven't had a chance to get out there and do that. And the good news is I don't have to drive anywhere today. All right, if I missed hydrogen, did I correct that mistake? Someone just emailed me. If not, let's see something. Nope, this structure is correct. This one. So anyways, let's get back to this one. I think you're all done. What's different? What's not a carbon-carbon single bond or carbon-hydrogen atom? Double bond. What am I reacting with? H plus and water. Remember water, think of as HOH, hydroxyl group. Break the pi bond. One carbon gets H, the other gets the OH from water. And it follows Markovnikov's rule. And now it's a ring. Now we have to figure out how many hydrogens there are on each carbon. This one has 3 bonds to it. There should be 4. And 4 minus 3, there's 1 hydrogen there. This one has 1, 2, remember double bond counts as 2 bonds, 3, 4. 4 minus 4 equals 0. This has 0. Do we break carbon-carbon single bonds? No. So the methyl group, CH3, are still in the ring. The ring is still in one. The hydrogen goes to this carbon. The hydroxyl group goes to this carbon, which one way you could have written it is this way. If you also could have written it this way. And for this class, they're identical. And that's how you do Markovnikov's rule when unsymmetrical addition. And it is very important to be able to make molecules like this, which you can use as is or not with this molecule specifically, but to make other things that we use in our daily life that could save people's lives even, or make them more comfortable. All right. Now, it turns out, and let me be honest with you, I always am, there are a lot of other reactions I could talk about with double bonds. However, we only have 16 weeks, we actually lost a week, 15 plus last week, finals week, which is not truly a finals week, but when we have our final. And I have decided long ago when I started teaching this course what do I spend more time on? And I'm spending time on some important reactions of double bonds, but later on, I like to have more time to spend things that would be more important to you, like carbohydrates, proteins, amino acids, fats and oils, fatty acids. So there are other reactions, but let's move on to alkynes, triple bonds. Now, an alkyne is a triple bond. And a triple bond, you should know, has 2 pi bonds and 1 sigma bond. So triple bond has 2 pi bonds and 1 sigma bond. Now, it's an acyclic unsaturated hydrocarbon with 1 or more triple bonds, and the bond angle of a triple bond is linear, it's straight. And I haven't talked about, and let's go back, about nomenclature of triple bonds. For unlike double bonds, for triple bonds, we use a YNE ending. Forget about diines, I don't talk about it. And when you do this, just like a double bond, you have to find the longest chain that has both carbons of the, in this case, triple bond, and use that to name, find an alkane, then you'll change it, and I'll show you. Now, you number it from the end, there won't be multiple bonds. And just like we did, indicate where the double bond was, and then give that the lowest number. And finally, do the alkyl groups just like we did it. So let's take a look at triple bond nomenclature. And here we have a molecule. What do we see that's different? A triple bond. So now we have to find what's the longest chain. There's only one, 1, 2, 3, 4, 5, 6, 7. And that would be, if it was an alkane, heptane. But you drop the ANE ending, and for a triple bond, the ending is YNE. So we have heptyne. YNE is a triple bond. Next, which carbon is closest to the end of the chain? We give that the lowest number. We start here, this is carbon 3. If we start on the other end, this carbon would have been 4, which is a lower number, 3 or 4. Time's up. Hopefully all pick 3. I hope so. And I'm done. You can't have cis-trans isomerism like you have in a double bond, because this bond angle is linear or 180 degrees. I'll never ask that on a test. And because of that, you've got to have a very large ring to have a triple bond in it. I think decades ago, someone did one of those papers like, ooh, look what I can do, which in my personal opinion, whoopee. Why'd you bother doing that? So you don't have to worry about cycloheptines, because I've never seen one in my career. You won't see one in your life. So remember, find the longest chain with both carbons of the triple bond, name it as an alkane, drop the ANE ending, put YNE, and then number which carbon of the triple bond is the lowest number closest to the end of the chain. Alks, the rest of the alkyl groups are the same. And it's your turn. Give the name, organic name, give the IUPAC name for the following molecule. And hopefully you've learned the table of the alkane names and the alkyl groups too. All right, let's do this. I think you're all done. Look for what's different, what's not a carbon-carbon single bond. In this case, triple bond. And it's an alkyne. How many carbons long is chain? 1, 2, 3, 4. That's butane, yeah, butane. I got it right. Wanted to say YNE. And you drop the ANE, butane, to YNE, butine. Now, what's the lead carbon closest to the end of the chain? Here it's 1. Here would be 3, which is smaller, 3 or 1. Hopefully, y'all pick 1, and it's 1-butine. And good news, I don't do enunciation quizzes. And here's one more for you to have fun with. Give the IUPAC name for the following molecule. Oh, I forgot to ask, is ever dreaming of a white Christmas? Wait until next December. I like snow, but not when I have to go play with my driveway with it. All right, I think everybody's done. I'll give you another 12 seconds. I'm looking at the clock I have here that does seconds. Let's do it. We have a triple bond here. Alkyne. How many carbons long is chain? 1, 2, 3, 4, 5, 6, or 5, 6. Either way, it's 6. That's hexane. Drop the ANE ending. It's a triple bond, and we use YNE ending. Hexine. We look at this and which carbon is close to the end. 1, 2, 3. If we start this way, 1, 2, 3, 4, which is smaller, 2 or 4. Hopefully, all pick 2. Therefore, to number this correctly, this is 4, 5, 6. Oh, look, it's your old friend, the methyl group. What carbon is it on? Carbon 5. So that'd be 5-methyl-2-hexine. And that's how you do it. Remember, you can't have it in a ring, so we don't have to do it. Now, there's 2 nomenclature skills. People are learning organic chemistry. You should have meaning types of questions I can ask on a test. And that is, here's the structure, give me the IUPAC name. And the other is, here's the name, draw the structure. And I'll do this one, then I'm gonna let you have some fun. And the question is, how do you draw this? You start from this end and move from the right, move left. Why on the ending? Tells you triple bond. If that were A and E, that would 9 carbons. So I better get to work. And then where is the triple bond starting at carbon 1? I'm going to define that as 1. And we have an isopropyl group. Where is it on carbon 3? 1, 2, 3, isopropyl. And there you have it. 3 isopropyl, 1 no 9. Again, start from the right, move left, Y on the ending tells you triple bond. This number in front tells you which is the lead carbon of that triple bond. And then we have the alkyl groups and where they are. I'm going to start using T-butyl instead of tert-butyl because in real life, organic chemists do that. And that's 4-T-butyl 2-decyne. Please draw the structure. It wouldn't say please on test, it would say draw the structure for the following molecules. 3 points each. I found when I do my test, I have questions that are smaller points instead of a few big points. Students do better. For those who came in late, in case anybody else did, sometime today or tomorrow morning, I'll be sending out an email. I'm postponing test number 1 by 1 week. I don't know what the date is, but it would be 2 weeks from today. Boy, the semester's going quick. And for those of you watching my video, thank me. Thank you. Thank me too. You can thank me, but thank you. You're making me a YouTube star. Nah. I think everybody's done. How do you decode this and know what to draw? You start from the right, move left. Y on E tells me triple bond. That were A and E decane, 10 carbons. So I better get to work. And where is that triple bond starting at carbon 2? This is 1, this is 2. This is 3. And on carbon 4, I have a tert or T-butyl group. And now it's time to put in hydrogens. And I'm done. And that's how you do it. Any questions? All right, let's look at reactions of alkynes, triple bonds. Good news, the two I'm going to cover, you've already sort of learned. And this is one way of writing it. I'll show you another way. Oop, not me. We have a triple bond, 3 lines, and we're reacting with hydrogen gas and a catalyst. And that catalyst can be, guess what? You've already learned this. Nickel, platinum, or palladium. Now, one thing is different. A triple bond has 2 pi bonds to break, so 1 sigma, which we don't break. Organic chemists are lazy. Why balance equations? I don't want to do that. So what we do to take care of this case, because in this case, you'll need 2 molecules of hydrogen. I'm not going to put that down. I'm going to do this. I'm going to do bracket, the letter X, the letter S, close bracket. And whenever you see bracket, letter X, letter S, close bracket, that's shorthand for excess. That means you have all the hydrogen in the world to react with other hydrogen, whatever hydrogen will act with. That way, we don't have to balance equations because we're lazy organic chemists. Now, what happens for each pi bond, each carbon, just like you saw in a double bond, gets a hydrogen, but they're 2 pi bonds, so each carbon gets 2 hydrogens. And if I were to ask if the organic product or products are the following, we'll look at the molecule. I'll do this one, and then after the break, I'll let you have fun too. We have what's different. Well, it's not a carbon-carbon single bond or a carbon-hydrogen atom. Oh, a triple bond. What are we reacting with? Hydrogen, but since I don't want to balance it, I'll put excess. And nickel is a catalyst. Remember the catalyst, which we abbreviate by CAT, equals nickel, can be nickel, platinum, or palladium. You break the 2 pi bonds, and each carbon of the triple bond gets 2 hydrogens. And do you break carbon-carbon single bonds? No, so I have 3. Here are my 2 carbons of the double bond, and each one gets 2 hydrogens. And now I'll put in the rest of the hydrogens. You could have written this CH3, CH2, CH3, or like that. Either way works for me. And with that, it's time to take a break again. I'll see you in 5 minutes. We'll do some more of this, and then we'll have our lab for today. time to get going. I hope you like my whistles and everything. This is a train whistle. One of my hobbies is model railroading. This I got in high school. I thought it was the neatest thing. This whistle was used, I don't know if they still do, by the bellman at hotels in Chicago to get a cab, who's ever next in line. And this they don't make anymore. The company that does this, I haven't used it yet. I love that. All right, let's get back to triple bonds. Now, I just showed you hydrogenation of an alkyne triple bond, break the pi bond. Did I give you an example? Hold on a second. No, I didn't. Bad Dr. White. You've got to have some fun too. I almost cheated you out of some fun. Bad Dr. White. And there's some fun for you. Give the organic product or products for the following reaction 3 points each. And after test number 1, you'll understand why I say these things. Also makes it more relevant for you. And remember, if you ever have a question, always feel free to ask in my class, or even when we're not in my class. Speaking about that, don't forget tonight from 5 to 6:15, I'll have my office hours. If you have any questions, come on by. And afterward, I'm going to spend some quality time with my driveway and snowblower and the front walk too. All right, let's get to work. When we look at a molecule, see how it reacts, look for what's different. What's not a carbon-carbon single bond? Oh, a triple bond. And what are we reacting it with? We're reacting a triple bond with hydrogen. And notice I have excess. And all that means is I have all the hydrogen in the world that will react with anything hydrogen will react with. And platinum is a catalyst. And I could have had nickel, I have platinum or palladium. And you break the 2 pi bonds, and hopefully all know a double bond has 1 pi bond, a triple bond has 2. Ooh, that's a good general knowledge question. And you break 2 pi bonds, and each carbon of the triple bond gets 2 hydrogens. Well, do you break carbon-carbon single bonds? No. So I have 1, 2, 3, 4, 5 across. I'll have 5 carbons across there. This carbon has a methyl group, which will still be there. Were my 2 carbons of triple bond? These 2, notice I broke the 2 pi bonds, 2 lines, and each one gets 2 hydrogens. And now I know there's 4 bonds to carbon. So I can put in the rest of the hydrogens. Now, if you wanted to write those two as CH2, that would have been fine. And that's hydrogenation of an alkyne. And let's move on. Uh-oh. Yep, it does it. Be with you in a second, maybe 3 seconds. All right. Sorry about that. I've got so many things going on. It does that every once in a while. All right, back to work. Next, let's talk about halogenation of an alkyne. You already learned this, but that was for a double bond. And remember, we have a triple bond. Now I can write it this way, or I'll do it a simpler way for you. And that is if I have a triple bond, remember that's 2 pi bonds, a 1 sigma bond. If I react it with a halogen gas, now once again, and let me give myself more room. I got more room now. I don't want to balance this. I'm a lazy organic chemist. So I'll use bracket, the letters XS, close bracket. That means I have all the halogen in the world I ever need to react with anything that a halogen gas will react with. And for this reaction, remember, X can be fluorine, chlorine, bromine, or iodine. And now, since we have 2 pi bonds, each carbon of the triple bond gets 2 halogens. And if we look at the following reaction, while you're copying it down, all right, I don't know if I mentioned it, but let's do it next Monday, the beginning of lecture. I will go through my method, how to eliminate test anxiety for the whole class. I will cut it out of video. If you want to learn it, come to my office hour. Can't come to my office hour, let me know. We'll set up a special time where you'll learn that, but it does help students a lot. All right. Let's look at this reaction. And it's my turn to do it, so I'm going to do it. What's different? What's not a carbon-carbon single bond? Oh, a triple bond. I'm reacting with excess chlorine. Chlorine is halogen. Excess, this tells me I have as much halogen as I'll ever need to react with anything that will react with. Remember, for this reaction, X is fluorine, chlorine, which it is in this example, bromine, or iodine. You have 2 pi bonds, you break them. Each carbon of the triple bond gets 2 halogens. And now, do you break carbon-carbon single bonds? No. So I have 1, 2, 3, 4, 5 across. 1, 2, 3, 4, 5 across. Which carbons were my carbons of the triple bond? Those 2. And each one gets 2 halogens. In this case, that's chlorine. I know there's 4 bonds to carbon. Oops, let me fix that finger. And I injured that finger years ago in a nunchuck accident. No, not really. Even though I do own 4 pair of nunchucks, my hobby is unusual weapons. I don't own any guns. All right, your turn. Have fun. Give the organic product or products for following reaction. 3 points each. You haven't realized that you're doing organic chemistry, and hopefully it's not that bad. It's fun. All right, looks like everybody's done. So I better get to work. And how do you answer this question? Give the organic product or products for this reaction. You look at the molecule, look for what's different, what's not a carbon-carbon single bond. Ooh, a triple bond. What are we reacting with? Fluorine gas. That's the halogen. We have excess, which means we have all the halogen gas we need to react with anything a halogen gas will react with. Pi bonds. And X can be fluorine, which in our case, chlorine, bromine, or iodine. And you break the 2 pi bonds, and each carbon of the triple bond gets not 1, but 2 halogens. Do you break carbon-carbon single bonds? No. So I have 1, 2, 3, 4 across. I have my 2 methyl groups here. Here are my 2 carbons of the triple bond, which are these 2. Each one gets 2 fluorines. And now I know there are 4 bonds to carbon. This looks like it's coming right at you on the screen. Didn't know I'm in 3D, and you don't need the glasses. And each halogen counts as a bond. And we're done. And that's how you do it. And again, making molecules like that, organic chemists like me use that to do other things as building blocks for other molecules. Now, when I was hired as a PhD organic chemist, no company is going to hire me or even a bachelor organic chemist and ask them to work. Can you work for us and tell us if I mix this and this together, what will I get? No, but you need to know those key reactions, those maps, general reactions to do the following. how do I make the following molecule? That's called synthesis. And I'm very biased. That's the best part of all organic chemistry. How do you make stuff? And that's what I've done my adult life in the chemical industry. And I still do that as a consultant. So let's look at a synthesis. Now, synthesis is a lot harder than just give the organic product or product. And if I were to ask you something like this, and I'm going to help you out if I put this on a test, what would be the starting material? Remember, this part of the area, academic chemists call that the reactant or reactants. I come from industry, which we call that the starting material. Or if there's more than one materials. And how do I do that? Well, you do the same thing you've already done before. Look at this molecule and say what we're trying to make now. What's different? What's not a carbon-carbon single bond or carbon or hydrogen atom? Ooh, look, 2 halogens. And notice they're on, it's called adjacent, 1 carbon next to another. And what are we reacting this question mark? Starting material, chlorine gas. And we know that's a halogen. And what do you start with? A double bond. And this is a reaction hint, you know. So what does that tell me? Notice I end up with 1, 2, 3, 4 carbons. Do you break carbon-carbon single bonds? No. So I have to start with 3 carbons, 4 carbons. Oh, did I lose one? Bad, Dr. White, 4 carbons. Now, the 2 carbons with the halogen, chlorine, are the 2 carbons of the double bond. The 2 carbons of the halogen are the 2 carbons of the double bond, which would be these 2, which means I've got a double bond there. Everybody with me? And now I know there are 4 bonds to carbon, so I can and that's how you do it. And if we were to take this compound and react with chlorine, we're going to get this molecule. And that's the fun part of organic chemistry. Now, at my level, it's like a chess game going backwards. Sometimes you have to go back, do 4 or 5 steps to get to where you want to get to. And something I won't teach in this class, but I had to learn, I know quite well, is not only how do you make it, but how do you make it so the price is under a certain amount? That's called the direct cost. That's called knowing cost accounting. All right. Now, sometimes we'll start with more than one starting material, and I'm going to help you out on when I took it. My instructor didn't do this, but I do it. Question mark means you start with one thing, react it with this, and you're going to make that. And the question here would be, give the organic starting material. Once in a while, I'll put down reactants, but I don't think I will this semester. And I'll put an S in case there's more than one for this. And now we're doing high level organic chemistry. Am I happy? I'm a happy camper when we do stuff like this, and I do stuff like this. All right. I think everybody's done, but let me shoot my poll out to you. All right, so what's different? Look at this molecule. What's that? A carbon-carbon single bond, carbon hydrogen. Ooh, not one, but two bromines. They're on adjacent next to each other carbons. Reacting with halogen gas. What do we start with? A double bond. Remember, X can be fluorine for this reaction, chlorine, bromine, which it is, or iodine. Now, do we break carbon-carbon single bonds? No. So I end up with 1, 2, 3, 4, 5. I better start with 5. The two carbons with the halogen are the two carbons of the double bond. These two carbons. So that means I have my double bond. I can draw it, good. And I know there's 4 bonds to carbon. And remember, double bond, and that's the molecule you get. And that's how you do it. Now, these molecules, these type of synthesis problems for you are much more difficult, they are, than give the organic product or products, which is also important to know. As of this date, the Supreme Court of the United States has still outlawed cruel and unusual punishment to students by instructors. So on test 1, I will only give one synthesis problem, but I can ask it for any general reaction I have covered. For test 2, I do 2 or 3. Test 3, I do 2 or 3. Test 4, not many. And the final, I do about 4 or 5. If I did any more, that would be cruel, unusual punishment. I think it's still illegal, so I don't. But that's, in my mind, the fun and most significant part of organic chemistry. But I'm biased. I'm a synthetic organic chemist. Remember, synthesis or synthetic is a fancy word for to make. And that's my training, how to make molecules. And if I look at the clock, guess what time it is? It's lab time, time for our first lab. Now, because I'm making up time lost because we didn't do the first week, normally I would have just gone 50 minutes, take a 5-minute break and do the lab, and you get out early. But we do that face-to-face too. So you get the same amount of lecture time from me. All right, everybody see Chem 170 G2L on your screen? Thumbs up, people. Thank you. Now, one of the things you have to know how to do is go to the assignment area. And on the top here, it says assignments. Click on it. And let me go to student view. click on assignments, and you'll see different assignments. Hopefully you all finish. Remember, get your signature sheets to me before test 1. Now, here's the lab. And I have it both as a Word document, DOCX, and a PDF file. Now, later on, after you finish answering the questions for this lab, you have to upload them to this lab, the assignment area. And if you don't own a scanner, which some of you don't, I do, but you may not, there's a great app a student of mine found for me about 2 years ago when we started doing this, and that is called Cam Scammer. Do not buy the one with the bells and whistles. You don't need to spend money. Use the free version. And I have here a document that explains how to use it, how to get it. And then once you, with Cam Scammer, you can make a PDF file. Then here are instructions how to upload it to here. Labs are due the following week. So the lab we're going to do now is due next week. Labs are easy points. I'm not a tough grader on the lab. Put something wrong down, I'll mark it wrong, but I don't sit there. How can I take points away from students, show how rough I am? No, lab should be fun. You should be able to get the points easily. Most students do. But you got to hand in the lab report. All right, let's look at lab number 1. But before we do that, many years ago, yeah, this is many years ago, back when I had more hair. But anyways, when I inherited, started teaching Chem 170, I looked at the labs that were in use, and they were pathetic, awful. And I challenged myself. You're an organic chemist. You've had decades experience in the chemical industry. Write new labs. Because one of the problems is when I inherited this, and I haven't changed it for reasons I'm not going to go into today, the lab is only scheduled for 1 hour and 50 minutes. At COD, when I teach the identical course called 1212, that lab is 2 hours and 50 minutes, a whole hour more. And because of that extra hour, we use at the other school a lab book that's printed because the labs take longer. So I had to come up with labs that are educational, and part of the thing I challenged myself, fun for you to do, and you could do in 1 hour and 50 minutes because students could have, I couldn't go 2 hours or more because some students at the end of the lab have other classes to go to or were. And let me open the first lab. And all the labs I do, I normally have what I call a setup. Where I talk about the labs or what you would be doing if we were face-to-face. And this is the lab you can download from D2L. And this lab deals with melting points. And in organic chemistry, there are certain tests that are very important. And one of the first tests we do for molecules that are solids are melting points. Melting point is when a solid goes to a liquid. And they're very important. Now, how do we determine a melting point? Now, inorganic molecules have very sharp melting point. I think you've all heard water melts at 0 degrees C, centigrade or Celsius. Celsius is the newer term. The old one was centigrade, which when I was a student, or even part of my adult life, we used, but a number of years ago, they changed over to Celsius to honor someone. And the water melts at 32 degrees Fahrenheit, very sharp. Organic don't. Now, what do you have to see to know the melting point of an organic molecule? You have what's known as the starting point and the end point or finishing point. PT is short for point. What's the starting melting point? When you heat a sample, we have what's called melting point equipment, a little tube that you put a sample in, you heat it up, and you have a magnifying glass. When you see any liquid, that's the starting point. The end point is the sample is all liquid. Therefore, if you had compound X and you're heating it up, and we have digital thermometers, it's called thermocouples, hooked up the meter. When you see at first any liquid, you record that temperature. Say it was 101. And then when the sample was all liquid, say it was 103, this would be your melting point. Of that compound X. Am I clever on names of compound? Not. Anyways, that's how you do it. Again, starting temperature is when you see any liquid in the sample. End point is when it's all liquid. Now, because you have this thin capillary tube, you just want to put the minimum amount of sample in there. And I show you that if we were in lab. Unfortunately, we're not. And you don't want to have too much because that's going to mess up your melting point. Because if you have a ton of stuff in there, it's going to take longer to melt. And guess what? You're not going to get valid results. And the other thing is when you're heating up the sample, you don't want to do too quick because temperature will be way past when it's all liquid. In other words, like when you driving too fast, you might run a stoplight or a stop sign. Please don't ever. So sample size and the rate at which you heat up the sample are important for accurate results. Sample size and the rate at which you heat up a sample is important for accurate results. Now, what's the reason chemists, organic chemists especially, do melting points? Good question. And here, chemists use melting point to determine either the identity of an unknown organic molecule or the purity of an organic molecule. So you should know, and I have questions you'll have to answer, and I give you all the information so you can answer those. And why do chemists do melting points? One is to determine ID. And the other one is to determine purity. Now, how do you do ID? Well, if you have a melting point in what's called the literature, published results for melting points of different organic molecules. If you think you know what you made, you can look up that compound if it hasn't been made before. And my melting point is the same as that. I think I got what I wanted. And that's how you do ID. For my PhD thesis, I did about 160, made about 160 new molecules. I think 140 of them or more were solids. So I did a lot of melting points for my thesis, also a publication from my thesis. And that helped other chemists because I identified molecules that I proved other ways what they were. That's important. Now, the other one is purity. And to talk about purity, I have to talk about the colligative effect. And I don't know if you remember or learned this in general chemistry, but the colligative effect is when you bring two molecules together, mix them together, samples, if they have the same melting point but are different, the melting point goes way down from the individual melting point and it gets wider. Again, colligative effect, the melting point, when you have two different molecules and they can have the identical melting point, when you mix them together, the melting point goes way down and it gets wider. Now, one of the things I tell students when I teach these labs is, part of the thing is organic chemists do, and other chemists also, we go into the lab and prove things. And this lab stuff, I'm telling you, if we'd been at ECC, I'm going to give you the data so you can find out. But you'd find out, am I lying to you about this stuff? I'm not, but who knows, I might be. So how do we use the colligative effect? Remember, melting point shows one, helps us find ID, and two, purity. Now, if you make a chemical like a drug and it's supposed to be a pure chemical, and you know the melting point, if you take the melting point of that pure compound, which you think is pure, and if it's lower and wider, you know it's not pure. Again, if you make something that you already know the melting point of, and what you make, you measure, if that melting point isn't the same as the literature value, you know it's not pure. Now, we can use purity and the colligative effect to determine ID. How do you do that? Say you have sample A. MPT is abbreviating for melting point. And the melting point is 107 to 109 degrees C. And you don't know what sample A is. And you think, oh, I know something. It's called compound Y. And that has a melting point 107 to 109. If you mix equal amounts of A and Y together, if they're the same, then there should be no change or very minor change, experimental error. When you do melting points, sometimes you'll be off by a degree or two. There should be no change in the melting point. If they're different, the colligative effect will kick in and it'll be lower and wider. And this lab, you do that. So let's take a look at the lab. Remember, you can come back and look at the video of that or come to my office hour. Remember, there's no such thing as a dumb question. You can ask questions about anything you do in my class or have to do. The only time I don't, well, I answer questions during a test, but I won't give you the answers for the problem. But if you have a question about what should I be doing, I accept that even during the test. I do that face to face also. So in today's lab, I would be teaching you how to put a sample into the sample tube. We're not there. I'd show you how to put it in the melting point apparatus, slowly turn up the heat of the temperature ramp, increase, and you'd look through a little magnifying glass, and we'd do some known. And then to make it interesting, I have an unknown. So let's talk about today's lab, what you would have been doing. We were face to face. And by the way, I'd highly recommend watch this YouTube video, especially from 5 minutes and 42 seconds to the end, to see how you actually do a melting point. Now, the procedure, we pulverize. You always want a powder, and you do that in a mortar and pestle. I have some downstairs that are crystal that I bought for my collection. And then you put it in. You just want a little bit, because remember, if you have too much, that's going to throw your melting point. You insert it into a sample, and I tell you, don't touch, and then you heat it. And then what you'll do is heat it at a short, a gradual rate. I'll never ask, quick time out for a second. One of the things I've done from the start when I taught this class, lecture and lab are separate. There will never be on my hourly exams or the final any questions from the lab. Good news, I don't do lab quizzes or lab finals. Your whole labs will be by answering the questions in the lab reports, and they're quite simple, and you'll see that. And you'll repeat this sample. You'll keep on heating it till you see the first bit of liquid. You report that temperature, and then the second when it's all liquid. Now, in lab, you would have done biphenyl, benzoic acid, urea, and tranexamic acid. These you would have done. This is teaching you how to do a melting point. Now, I have a 50-50 mixture of tranexamic acid and urea. Notice both of these, if you were to do it, have the same melting point. And if you'd gone into lab, students get something like this. And notice they're different. The colligative effect is true. The melting point is lower and wider. I didn't lie to you. Yay. All right, now to make it interesting, you're going to be doing an unknown sample and determining the identity. And the way you do it is you first do the melting point as unknown. I call it for this lab A. And I tell the students, guess what? The district attorney of Kane County has asked us, what's the identity of this unknown? Because once we know that, or he knows, or she knows that, I don't know who it is, then they can convict this heinous criminal of this very terrible crime. I'll let you fill in the blank. What was the terrible crime? So we have to, and you have to, and what you would have done in the lab is get the melting point. Now, in real life, students like you who do melting points, I've done hundreds of them. I don't even know how many. But rookies like you, you're usually going to be a little lower, and maybe even a little bit wider than the published or correct results. And I understand that. So I have data in here like in real life. And you get a number 118 to 120. Now, to use the colligative effect, you'd mix it with a couple of things to see where does the melting point not change. And compound A is one of these 4 compounds. And if you mix it with benzoic acid, it's this temperature. If you mix it with cinnamic acid or tranexamic, it's this temperature. And you have to fill in right here which one you think the identity of A is. Don't say it now and don't give it away. This is part of the lab. You have to end in a week from today. But if in real life you would have been doing these melting points, it takes about an hour, and about now you'd be finishing up with the lab. I wouldn't have gone as long as I did. Now, you have to also answer these questions. 1, 2, 3, and 4, and 5, and that's it. Next week, you have to, by next Wednesday, end of the day, you need to upload these answers. Plus, the only thing up here is what's the identity of the unknown compound. Now, if you don't own a printer, and last November, my old printer died. I had an HP4, and finally was telling me, get rid of me and buy a new one. And I did. I got a nice HP printer. It's black. It's a LaserJet black and white. I don't need color. It's about $200 from Staples. If you need one, it's a good one. I've been using it since, was it last? No, it was a year ago, December. I've been using it for a whole year. I'm sorry. Time flies when you're having fun with your printer. But anyways, you can handwrite these out. And same thing with the questions. You don't have to write the actual questions. Just put down questions, number 1, your answer, and so on. And that's today's lab. If I look at the clock, we're essentially done for today. And we've done our organic chemistry. You've done your lab. And with that, it's Wednesday. So I'm going to not see you unless you come to my office hour tonight till next Monday. All right, listen carefully. We have finished a chapter for alkenes and alkynes. Next Wednesday, I will go through the problem set for alkenes and alkynes. So I highly recommend between now and next Wednesday, you try it first. That's how you get good grades on my test and this class, which I hope you all do. With that, I'm going to say gang gesund, which is Yiddish for going health, which since the pandemic started, I've been doing that. Gang gesund. Goodbye now. I stole that from Granny from the Beverly Hillbillies. If you don't know what that is, look it up on YouTube. You've never seen a Beverly Hillbilly? Oh, you're missing stuff in life. Boy,